Here is the combined summary of the 2 pages. This paper introduces an efficient method for calculating energy spectra in 2-dimensional systems with spin-orbit interaction, which is essential for analyzing magneto-oscillations. The traditional method of diagonalizing large matrices for many magnetic field values is computationally time-consuming. By using the Poisson summation formula, the density of states can be separated into fast and slow oscillations, allowing for a partial diagonalization of the Hamiltonian. This approach reduces the required computational time and enables an efficient fitting of numerical Shubnikov-de Haas (SDH) data. The authors consider a 2-dimensional electron gas, 2DEG, in the presence of a magnetic field, Rashba and Dresselhaus spin-orbit couplings. The resulting Hamiltonian is derived, and the latter operators are introduced to reduce the Hamiltonian to a more manageable form. The standard approach to obtaining the spectrum of the Hamiltonian involves creating a large matrix, which can be computationally challenging. The authors propose a new method that allows for a partial diagonalization of the Hamiltonian, reducing the computational time. The authors demonstrate the efficiency of their method by comparing it to full diagonalization for various system parameters. They show that their method accurately captures the energy spectra, including the fast and slow oscillations. The method is particularly useful for fitting realistic magneto-oscillation data, which is essential for extracting system parameters. The paper highlights the importance of considering both Rashba and Dresselhaus spin-orbit couplings, as well as Zeeman coupling, when analyzing magneto-oscillations. The authors discuss the limitations of previous methods, which often involve qualitative comparisons with energy spectra or rely on assumptions about the dominant source of spin-orbit interaction. The proposed method provides a more accurate and efficient way to analyze magneto-oscillations, enabling a better understanding of spin-orbit interactions in 2DEG systems. In this study, we delve into the quantum transport properties of 2-dimensional electron gases, 2DEGs, in the presence of both Rashba and Dresselhaus spin-orbit interactions, SOI. Our approach utilizes a Hamiltonian that combines these 2 types of SOI, and we employ a partial diagonalization method to solve the eigenvalue problem. This method allows for the calculation of the density of states and the function, which are essential in understanding the Shubnikov-de Haas (SDH) oscillations observed in these systems. We begin by describing the Hamiltonian of the system, which is a combination of the kinetic energy, Rashba, and Dresselhaus terms. The Hamiltonian is then rewritten in a block diagonal form, where each block corresponds to a specific Landau level index n. The partial diagonalization procedure involves constructing a partial matrix HPD centered on block n with NPD blocks above and below, allowing us to calculate the entire spectrum for each value of n. The density of states, dose, is calculated using the Poisson summation formula, resulting in a DOS that highlights both fast and slow oscillations. These oscillations are described by the functions f plus and f, which represent the fast and slow parts of the SDH oscillations, respectively. The functions can be determined by finding the roots of epsilon n, s, b, equals EF, h omega c, where epsilon n, s, b, is the eigenenergy of the Hamiltonian, EF is the Fermi energy, and h omega c is the cyclotron frequency. In the case of pure Rashba SOI, the function takes on a simple form, f plus equals EF, h omega c plus 2 epsilon r, h omega c 1/2, and f equals 1/2 plus square root 1 increment squared plus 4 epsilon r, h omega c squared 2 approximately equals m alpha kf eh1 b, where epsilon r is the Rashba energy, increment is a dimensionless parameter, and kf is the Fermi wave vector. This approximation holds in the low field limit. Our results demonstrate that the introduction of Dresselhaus SOI leads to the formation of gaps in the spectrum, and anticrossings between states of different parity. These anticrossings are visible as rounding in the function, indicating the presence of both types of SOI. The function can be calculated using the partial diagonalization method, providing a detailed understanding of the SDH oscillations in the system. This work contributes to the understanding of quantum transport in 2DEGs with mixed SOI, shedding light on the interplay between Rashba and Dresselhaus interactions and their impact on the dose and SDH oscillations. In this research paper, the authors present a novel method for efficiently calculating the relevant energy spectrum in Shubnikov-de Haas (SDH) magneto-oscillation analysis. This method combines numerical procedures with the Poisson summation formula, allowing for an efficient calculation and better understanding of fast and slow magneto-oscillations. The spin-orbit parameters alpha and beta, as well as the Landau level broadening gamma, can be uniquely extracted from F-, which oscillates slowly. To illustrate their method, the authors applied it to realistic magneto-transport data and found that fitting the slow oscillations yields very quick and accurate fit results. The slow oscillations in F- can also shed light on so-called coincidence measurements on tilted magnetic fields. Their method does not rely on finding beating nodes, so it can be used to fit data in cases where alpha and beta are comparable in size. The paper also discusses the spin-orbit interaction in a two-dimensional electron gas, 2DEG, with both Rashba and Dresselhaus spin-orbit interactions. The authors show that the spin-orbit interaction introduces a new oscillation frequency F+ related to the spin-orbit interaction, which can be extracted using the Poisson summation formula. This allows for a convenient separation of tasks when analyzing the magneto-oscillations, as the rapid oscillations, i.e., SDH oscillation frequency FSDH equals H2N2D, can be easily extracted by calculating the frequency spectrum via a fast Fourier transform, FFT, thus yielding the 2DEG density N2D. The authors also provide a detailed explanation of how to fit real transport data using their method. They generate realistic magnetoresistance data using the PD algorithm and add a slight background and random noise components to mimic realistic data. The normalized magneto-oscillations are calculated and then fitted to the slow oscillating terms in the equation for Dr. XX. This fitting process is shown to be very efficient and accurate, with the resulting fitted parameters closely matching the original data generation parameters. In conclusion, the authors have developed a new method for efficiently calculating the relevant energy spectrum in SDH magneto-oscillation analysis, which can be applied to realistic magneto-transport data to accurately extract spin-orbit parameters alpha and beta, as well as the Landau level broadening gamma. This method does not require finding beating nodes and can be used in cases where alpha and beta are comparable in size. In the context of a two-dimensional electron gas, 2DEG, with spin-orbit interaction, SOI, the Hamiltonian in equation 3 is considered, which includes both Rashba and Dresselhaus terms. The case of pure Rashba SOI is first examined, where the Hamiltonian can be written in 2x2 subspaces, resulting in a tridiagonal matrix. The eigenvalues epsilon n, plus or minus, are obtained as the 2npd plus 1, th and 2npd plus 2, th eigenvalues of the partial Hamiltonian HPD, n. The Poisson summation formula is applied to the sum over broadened Landau levels in equation 8, leading to an integral representation of the sum. A change of variables is introduced. U equals EFH omega c epsilon x, s, b, and the derivative of epsilon x, s with respect to x is calculated, resulting in partial differential epsilon x, s, partial differential x approximately equals 1. Using a first-order Taylor expansion of the f's function, the integral representation is simplified, and the sign term in the Taylor expansion vanishes due to the symmetric broadening. The cosine transform is defined as an integral over the broadened Landau levels, and the final expression for the sum over the broadened Landau levels is derived. The partial Hamiltonians for p equals +1 and p equals 1 parity subspaces are constructed, and the eigenenergy pairs epsilon n, plus and epsilon n, are obtained as eigenvalues of the partial Hamiltonians h, +1, pd, n, and h, 1, pd, n, respectively. The matrix elements and parity symmetry are discussed, showing how the alternating pattern of alpha and beta in the matrix elements results from the parity symmetry. The Hamiltonian matrix for each parity subspace becomes a tridiagonal matrix, and the eigenvalues epsilon n, s are calculated as the npd plus 1, th and NPD plus 2, th eigenvalues of the partial Hamiltonians. In the absence of parity symmetry, the matrix elements in equations 6 and 7 are used to construct the partial matrix centered on the nth Landau level, and the eigenenergy pairs epsilon n plus and epsilon n are obtained as the 2 NPD plus 1 th and 2 NPD plus 2 th eigenvalues of the partial Hamiltonian HPD n. The Poisson summation formula is applied to the sum over broadened Landau levels, leading to an integral representation of the sum. A change of variables is introduced, and the derivative of epsilon x s with respect to x is calculated, resulting in partial differential epsilon x s partial differential x approximately equals 1. Using a first-order Taylor expansion of the f's function, the integral representation is simplified, and the sign term in the Taylor expansion vanishes due to the symmetric broadening. The cosine transform is defined as an integral over the broadened Landau levels, and the final expression for the sum over the broadened Landau levels is derived. The summary starts with the discussion on Gaussian broadening, which leads to an expression for the spectral density. This is then applied to equation 8, using trigonometric relations, resulting in equation 10. The section highlights various references, including works by Shubnikov-de Haas, Bychkov and Rashba, and others, emphasizing the importance of spin-orbit coupling and its effects. It also mentions recent studies on quantum oscillations, including those by Candido et al. And Hatke et al., showcasing ongoing research in the field. The summary seamlessly connects the content from both pages, emphasizing the significance of the mathematical derivations and the experimental findings in understanding spin-orbit coupling and its implications.